Alright, Lesson 8, the difference between theoretical probabilities and estimated probabilities. So have you ever watched the beginning of the Super Bowl game? After the traditional handshakes, a coin is tossed to determine which team gets to kick off first. Whether or not you are a football fan, the toss of a fair coin is often used to make decisions between two groups. So let's take a look at examples 1 through 9. Coins were discussed in previous lessons of this module. What is special about a coin? Well, in most cases, a coin has two different sides, a head side, or heads, and a tail side, or tails. The sample space for tossing a coin is the set of heads and tails. And notice how we use the squiggle brackets to indicate a set. If each outcome has an equal chance of occurring when the coin is tossed, then the probability of getting heads is 1 out of 2, or 5/10, or 50%. The probability of getting tails is also 1 out of 2, or 5/10, or 50%. Note that the sum of these probabilities is 1. The probabilities formed using the sample space and what we know about coins are called the theoretical probabilities. Using observed relative frequencies is another method to estimate the probabilities of heads or tails. A relative frequency is the proportion derived from the number of observed outcomes of an event divided by the total number of outcomes. Recall from earlier lessons that a relative frequency can be expressed as a fraction, a decimal, or a percent. Is the estimate of a probability from this method close to a theoretical probability? Well, the following example investigates how relative frequencies can be used to estimate probabilities. So Beth tosses a coin 10 times and records her results. Here are the results from the 10 tosses. Are there other situations where a coin toss would be used? Well, a coin toss can be used to determine who gets to use the computer first, which team starts the ball in a basketball game, or for any other situation where there are two things to choose from. An interesting fact, in several state constitutions, if two candidates receive the same number of votes, the winning candidate is determined by a coin toss. Is it possible to toss a fair coin and get 3 heads in a row? How about 5 heads? Well, yes, it is possible, but not as likely as getting some heads and some tails. So is it possible to get several heads or tails in a row? And that evaluating how likely it would be to get 3, 5, or even 20 heads in a row are examples of probability problems. Begin working through examples 1 through 9. Check your answers as you go by continuing the video. So here's what you should have for example 1. Notice that as each time we continue, heads would be the 3 heads out of 4. So 3 out of 4 is 75 hundredths. And as you continue to get heads is 4. This would be 4 out of 5, and then 5 out of 6. But then when you get a tails, the 5 continues to be 5 because it's not a heads, but the toss continues to increase by 1. So now it's 5 out of 7, or 71 hundredths. Then 5 out of 8, so now notice that our probability is going down. And 5 out of 9, our probability goes down again. Then we do 6 out of 10, our probability goes up. And we keep doing this. So for the 10 tosses, if we have 0, and then they did the same thing here for tails. So you have no tails, so therefore no relative frequency. Then when you get 1 tail, it's 1 out of 3. Notice how that is the difference. If we added 67 hundredths and 33 hundredths, we would get a total of 1. So as this is going up, this continues to go down, and vice versa. Notice that 60 hundredths at the end added to 40 hundredths would give us a total of 1. All right, for part 2, so the sum of relative frequency of heads and the relative frequency of tails for each row is also 1. And if we were to graph this, your graph would look like this. Then Beth continues tossing the coin and recording the results for 40 tosses. Now instead of doing each one, we're just going to look at the number of tosses, 1, 5, 10, 15, and 20, and then count up the number of heads so far. So after 15 tosses, there are 8 heads, so 8 divided by 15 is 53 hundredths. After 40 tosses, there were 19 heads, so 19 out of 40 is 0.48 or 48 hundredths or 48%. And then graphing that as a table or as a graph from the table, you would notice that eventually this would start leveling out. And this is what 6 and 7 are talking about. As far as if you were to continue with the experiment, what do you think would happen? And here is the answer for number 9. Alright, so here's some history on people who wanted to observe long-run relative frequencies. Notice how for each of these cases, the relative frequencies were close to 5/10. You may also find it interesting that the relative frequencies were not exactly 5/10. So the French naturalist Count Buffon, who lived from 1707 to 1788, he tossed a coin 4,040 times. The result was 2,048 heads, or a proportion of 2,048 over 4,040, which is 0.5069 for heads. Around 1900, the English statistician Carl Pearson tossed a coin 24,000 times. The result was 12,012 heads, a proportion of 0.5005. While imprisoned by the Germans during World War II, a South African mathematician, John Kerrich, tossed a coin 10,000 times. The result was 5,067 heads, or a proportion of 0.5067. If they were closer to 0.5 than in our example, why do you think that was the case? So let's take a look at exercises 1 through 8. Beth received 9 more pennies. She securely taped them together to form a small stack. The top penny of her stack showed heads, and the bottom penny showed tails. If Beth tosses the stack, what outcomes could she observe? And what are the possible outcomes? Well, she would have heads, tails, and the stack landing on its side. These 3 outcomes represent the sample space. So for number 1, Beth wanted to determine the probability of getting heads when she tosses the stack. Do you think this probability is the same as the probability of getting heads with just 1 coin? Explain your answer. Well, the outcomes when tossing the stack would be the set of heads, tails, and side. This changes the probability of getting heads as there are now 3 outcomes. So for number 2, pretend that we are going to make a sturdy stack of 10 pennies in which one end of the stack has a penny showing heads and the other end tails. What is the sample space for tossing a stack of 10 pennies taped together? Do you think the probability of each outcome of the sample space is equal? Explain your answer. Well, the sample space is the set of heads, tails, and side. A couple of tosses should clearly indicate to you that the stack lands often on its side. As a result, the probabilities of heads, tails, and on the side do not appear to be the same. So here is a result from a sample experiment. Record the results in the table on your lesson worksheet. We have heads, heads, side, 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 tails, side, side, tails, side. So calculate the relative frequency of heads so far. Well, out of the first toss, 1 out of 1 is 1. In the second toss, 2 out of 2 is 1. But then for the third toss, we have a side, so now we have 2 out of 3, which is 0.67. Then 2 out of 4, which is 50%. 2 out of 5, which now brings us down to 40% or 0.40. 2 out of 6, which is now 33% or 0.33 repeating. 2 out of 7, which is 0.29. 2 out of 8, which is 0.25. 2 out of 9, which is 0.22. And 2 out of 10, which is 2/10 or 20%. So based on the value of the relative frequencies of heads so far, what would you estimate the probability of getting heads to be? Well, we would estimate the probability of tossing a heads as 0.20, or something close to that last relative frequency. So for number 5, toss a stack of pennies another 20 times. Here are the results. Complete the following table. So go ahead and fill this out on your lesson worksheet. Okay, you should be done copying this into your lesson worksheet. Summarize the relative frequency of heads so far by completing the following table. So we're not going to do it for each one, but you should be able to figure it out for 1, 5, 10, 15, 20, 25, and 30. So for example, out of 15 tosses, there were 4 heads so far, so we're at 0.27. And for 30 tosses, we ended up with 8 heads, so that would be 0.27. So based on the relative frequencies for the 30 tosses, what is your estimate of the probability of getting heads? Can you compare this estimate to a theoretical probability like you did the first example? Explain your answer. Well, it is estimated probability equal or close to the last value of the relative frequency column. For this example, that would be 27/100ths. An estimate of 25/100ths for this sample would have also been a good estimate. We cannot compare this to a theoretical probability because the theoretical probability is not known for this example. Factors that might affect the results for a long-run frequency include how much tape is used to create the stack, how sturdy the stack is, or how much surface area there is between the choices. So for an optional activity, if you would like, create another stack of pennies. Consider creating a stack of 5 pennies, 10 pennies, or 20 pennies taped together. Again, make sure that the pennies are taped securely or you might have a mess. Toss a stack you made 30 times and record the outcome for each toss. All right, let's wrap this up. When you toss a stack and calculate a relative frequency, are you getting an estimated probability or a theoretical probability? Well, you'd be getting an estimated probability. Is there an exact number of times you should toss a stack to estimate the probability of getting heads? Well, no, there is no exact number of times you should toss a stack. However, the larger the number of tosses, the closer the estimated probability will approach the theoretical probability of the event. All right, see you in class.